All right, let's take a look at exit slip 17. In this exit slip, we were reviewing log properties, specifically the product, quotient, and power properties, and also playing around with solving exponential and log equations. As we know by now, there are a wide variety of equations we can solve using exponentials and logs. So of course, the one problem that we'll look at here doesn't really cover all the types, but hopefully it will be a nice review. So for this first problem, we were asked to condense the log expression into one log expression. So another word for condense, we've used compress as well, just to clarify in terms of language. You can hear condense or compress. And so the goal of this problem is to take these three logarithmic terms and use the properties to compress it into a single log term. So a lot of times I like to start with just the power property. And what the power property does is it allows us to move the coefficients, you could say, of the logs on as exponents. So when we're compressing, that's a good starting point. So if we do just that much, we would have log base 7 of x cubed being added with log base 7 of x minus 1 to the power of 1/2 minus log base 7 of x plus 2 to the 4th. So if all we did so far was just use our power property, we would get that result. Now I'm just going to focus on the remaining operations. Oops, took away a little too much there. Of addition and subtraction. So let's just focus on the addition of the logs. We know addition is going to use the product property, and then we'll also focus together on the subtraction. So when two logs are being added, that means when we compress it to a single log, those arguments will be multiplied. So I'll really have x cubed multiplied by the x minus 1 to the 1/2 power. And when logs are being subtracted, as our last term is, that tells us we can divide by that argument. So I'll divide by the x plus 2 to the power of 4. So I think we've reached our goal of compressing into one logarithmic expression. I'll just offer one other way to write a final answer here, and then we'll move on to solving. One thing you may have noticed is we understand the power of 1/2 is the same as square rooting. So it wouldn't be a far fetch to rewrite it in this way. So either one of the answers we have at this last line would be great. All I did from one to the next is say that raising something to the power of 1/2 is the same as square rooting. So just want to keep us mindful of that. So either one of these would be great stopping points for this compressing or condensing problem. Cool. Those properties are helpful sometimes when we're solving. So sometimes you need to use the product, quotient, and or power property in the context of solving. Let's look at the second one. The second one asks us to solve. I'm just going to rewrite it. We're solving 7 to the power of 3t equals 100. And one of the solving techniques we've looked at thus far has been to make the bases match. So in this problem, if that were a possibility, it would mean that I could rewrite 7 and 100 as something, some base to a power. But 7 can't really be written other than 7. And although 100 is 10 squared, the base of 10 surely doesn't match the base of 7. So I don't feel like the bases matching strategy is going to be really helpful for us in this problem. It would be helpful if we had something like 4 to the 2x equals 16 to the x, because then I could rewrite 16 as 4 squared. So just real quick to build that strategy in context, that would be a case where making the bases match would work. But that's not where we are in this problem. So instead of making the bases match, let's think about introducing a logarithm to both sides so that we can use the power property. So I'd love to be able to take this exponent of 3t and pull it down out front. Of course, as it sits, that's not true. We can't just pull an exponent down and have it be equivalent. But if I had a logarithm out front of that term, then I would be allowed to do so. So the beauty of algebra, right, is we can choose to introduce a log on both sides, and we haven't changed the equivalency of our statement. So I'm going to take a log on both sides of the equation, and then for my next step, I will use that power property that we actually talked about in the first question. That brings down the power as 3t times log of 7 is equal to log of 100. And our goal being to get t alone is much more close at this point. T is currently being multiplied by 3 and log of 7, so I might as well just divide by both 3 and log of 7 to get t fully alone. So when I divide by 3 log of 7 on the left, that frees up t. T is left alone. On the right, an exact solution for this would be log of 100 divided by 3 log of 7. I think in the directions, though, it did ask for an approximate solution, so just pay attention to what we're looking for. This one said, it didn't say an exact solution, but the wording that says round answer to the nearest hundredth implies an approximate solution would be appropriate here. So normally in the homework, I just encourage you to stop at an exact solution, but let's go ahead and get an approximate answer for this one. I'm going to use Desmos, so I'm just going to plug this expression into Desmos. I'll show you as I do it, just so you can get comfortable using Desmos more yourself. And then we'll round our answer, as it said there, to the nearest hundredth, which means 2 decimal places. So in Desmos, I'm going to switch over and type log of 100. Log of 100 divided by 3 log of 7. And you can surely type this in on your calculator too. My only little tip for your calculator will be just be careful with parentheses. So in Desmos, you guys can tell that it correctly divided by both 3 and log of 7. If you're on a scientific calculator, you'll likely need to use parentheses for that whole denominator piece. So my decimal value is 0.78886, on and on and on. We're rounding to the nearest hundredth, so the 8 in the thousandth place will bump the 8 in the hundredths place up to a 9. So a good approximation there would be about 0.79. So we'll say that's our approximate solution rounded to the nearest hundredth. Just again to emphasize the types of solutions we're sometimes asked to find. If the directions had said give an exact solution, we would have stopped at the logarithmic expression here. And since this one said round, we're offering instead an approximate solution. Cool. So hopefully that makes some sense. The only other thing I'll tag on, just for being thorough, is I somewhat arbitrarily chose to use a log base 10. I introduced log without a stated base back here, so it's understood to be 10. I could have also introduced an ln to both sides or a log of whatever base I wanted. So just as a friendly reminder, whatever log you choose is just up to you. Just make sure you use the same type of log on both sides. So I'll leave it to you to plug in that approximate solution, make sure it checks, and hopefully we're getting more and more comfortable with solving these types of equations.